We will begin this lesson by learning about the integral zero theorem. In Part A, we'll define the integral zero theorem and answer the question, how is this theorem useful in factoring a polynomial? The integral factors of the constant term of a polynomial are potential zeros of the polynomial. Recall that in the general form of a polynomial, the constant term is placed at the end of the polynomial. The integral zero theorem is useful in factoring polynomials because it helps us find the zeros, which in turn give us the factors. Consider the polynomial p of x equals x cubed minus 3x squared plus 4x minus 6. Potential zeros of the polynomial are plus minus 1, plus minus 2, plus minus 3, and plus minus 6. Now consider the polynomial p of x equals x to the power of 4 minus 16. The potential zeros of the polynomial are plus minus 1, plus minus 2, plus minus 4, plus minus 8, and plus minus 16. The integral zero theorem is a special case of the more general rational zero theorem. The rational zero theorem helps you find fractional potential zeros for polynomials with a leading coefficient other than 1. In Math 30-1, you will only need to know how to factor polynomials using the integral zero theorem. Now we'll move on to Part B. Using the integral zero theorem, find potential zeros of the polynomial p of x equals x cubed plus x squared minus 5x plus 3. We can use the integral zero theorem to find potential zeros of this polynomial. The factors of the constant term 3 are plus minus 1 and plus minus 3. Therefore, potential zeros of the polynomial are positive 1, negative 1, positive 3, and negative 3. Now we'll move on to Part C. Which potential zeros from Part B are actually zeros of the polynomial? Recall that the potential zeros of p of x equals x cubed plus x squared minus 5x plus 3 are the factors of the constant term positive 1, negative 1, positive 3, and negative 3. Evaluate p at 1, p at negative 1, p at 3, and p at negative 3 to see which potential zeros are actual zeros of the polynomial. The work for each calculation is shown. Both 1 and negative 3 are actual zeros of the polynomial since p at 1 equals 0 and p at negative 3 equals 0. Negative 1 and 3 are not zeros since p at negative 1 and p at 3 are not 0. The zeros of p of x are negative 3 and 1. Now we'll move on to Part D. Use technology to draw the graph of p of x equals x cubed plus x squared minus 5x plus 3. How do the x-intercepts of the graph compare to the zeros of the polynomial function? The x-intercepts of the graph are negative 3 and 1. The x-intercepts match the zeros of the polynomial that we found using the integral zero theorem. The graph gives us information that the integral zero theorem does not, the multiplicity of each zero. The 0 of -3 has a multiplicity of 1, and the 0 of 1 has a multiplicity of 2. In part E, we'll use the graph from part D to factor p of x equals x cubed plus x squared minus 5x plus 3. Bring back the graph from part D. The x-intercept of -3 corresponds to a factor of x plus 3. There is just the one factor since the multiplicity is 1. The x-intercept of 1 corresponds to factors of x minus 1 and x minus 1. There are two identical factors since the multiplicity is 2. Using the graph, we have found all of the polynomial factors. If the leading coefficient of the polynomial is 1, and it is, the factored form of the polynomial is the product of the individual factors. This gives us p of x equals x plus 3 times x minus 1 times x minus 1. Combine identical factors to get x plus 3 times x minus 1 squared. Note that we can only factor this way when the leading coefficient of the polynomial is 1. The technique we just used to factor the polynomial is called factoring with technology, since we require a graphing calculator to see the graph and the multiplicity of the zeros. While factoring using a graph works some of the time, it does not work all of the time. As we proceed through this lesson, we will learn how to factor polynomials algebraically. This is a more general technique that will work even when the graph of a polynomial does not yield enough information for successful factoring.